You know, we use our computers for all this super complex stuff, right? But the other day, I was thinking about the absolute most basic things they do, like just adding two numbers. And it turns out, even a simple question like that hides some seriously brilliant engineering secrets.
So let's just ask it straight up. When your computer sees a line of code that says C equals A plus B, what's really happening under the hood? How does the processor physically take the value of A and B and smash them together to get the right answer?
I mean, the logical answer would be that it uses an instruction that's literally called add. Makes sense, right? But here's the crazy part. If you actually look at the low-level code that modern compilers spit out, you almost never see it. The most obvious answer is not the one they use. Instead of add, you see this thing. This is actual assembly code, the language that talks directly to the processor. And it looks pretty cryptic, doesn't it? There's no add anywhere. Instead, you've got this command, LEA, and that is the puzzle we're going to solve today. Okay, so what gives? This is the big question. Why would a compiler choose this weird roundabout instruction instead of the simple direct add command? Well, the answer reveals a really interesting limitation of the processor and an even more clever workaround. So to get why this happens, we have to understand the rules of the game that the processors are playing by. And for most of the processors in our desktops and laptops, the x86 family, we're living in what's called a two-operand world. And this slide really gets to the heart of the problem. You see, most instructions on these processors, including add, are two-operand. It's like saying A equals A plus B. The result of the addition gets stored back into A, which means the original value of A is just gone. It's destroyed. Now, this is a huge pain if you still need that original A for something else. What we really, really want is the version on the right, the three-operand version, C equals A plus B, where our original numbers, A and B, are kept perfectly safe. So how do compilers pull off that clean, non-destructive addition? Well, they don't get a new instruction. They get creative. And, well, they kind of abuse an existing one. Let's break down how this brilliant little hack works. And this brings us right back to our mystery command LEA. It stands for Load Effective Address. Now, its official day job is to figure out where something is in the computer's memory. It's built to do these slightly complex calculations like, okay, start at this location, then move forward by this other amount. Okay, think of it like this. You ask your GPS app for the route from your house to the store. It does all the math to figure out the final destination's address. But LEA does something pretty special. It calculates that final address, and then it just stops. It tells you where the destination is, but it never actually goes there. It just does the math and hands you the result. And that is the trick. The people who write compilers realized, wait a minute, the processor's hardware for calculating addresses is basically just a really powerful, really fast adder. So they thought, hey, why don't we just hijack that hardware? We can feed it our two numbers as if they were a base location and an offset, let it do the addition for us, and then just grab the result without ever caring about memory at all. It's genius. So when we look at that cryptic code again, LEA EAX from RDI plus RSI, we can see it's not about memory at all. It's a clever disguise. It's the compiler's secret, super efficient way of saying, hey, processor, take the number in storage spot RDI, add the number from spot RSI, and please put the final answer in a totally separate spot, EAX. It's our perfect, non-destructive C equals A plus B addition. Now, you might be thinking, okay, that's a neat little trick, but does it really matter? And the answer is a resounding yes. This isn't just a quirky alternative. It's a real, tangible optimization. And it's the reason why pretty much every modern compiler does addition this way. So here's the payoff. First off, using LEA for addition is extremely fast. Often it takes just one tick of the processor's clock. But the big one, of course, is that it's non-destructive. Our original numbers, RDI and RSI, are kept completely safe, ready for us to use again later. It saves us from writing extra code just to shuffle data around. It's a perfect example of the incredible hidden creativity that's humming away inside almost every program you run. And that just leaves you with this really cool thought. This is just one tiny optimization for one of the simplest things a computer can do. It really makes you wonder, right? What other hidden tricks, what other clever abuses of hardware are working behind the scenes right now to make the technology we use every single day just a little bit faster, a little bit more efficient?